Watson's division, where she leads the AI operations team with a mission to scale AI for enterprises.
Say done.
Rama heads the AI mission of enabling natural and personalized and compassionate conversations between computers and humans. She was named by Forbes as the top 20 women in AI research, has been featured in 18 and AI by Fortune magazine, and named top 10 pioneering women in AI and machine learning by Enterprise Management 360. Rama has worked on agent-based decision support systems, electronic marketplaces, and semantic web services, for which she led a worldwide Web 3 standard. Her incredible accomplishments include 4 book chapters, over 100 technical papers, 18 patents, 25 plus additional pending, and she's also a recipient of 3 Best Paper Awards in AI and Operations Research. She holds a Master's in Computer Science and also has received a gold medal from New York University for MBA. She has served as the president of ISSIP, a Service Science Professional Society, for 2018, and continues to drive AI projects through this society. Without further ado, I'm going to hand off to Rama to share her perspectives today. Thank you.
Thank you, Savita. Is my mic on?
Just start and I'll get you going. Just keep going.
Okay. Can you hear me okay?
I'll turn it on. Just give me a second.
Silence your phones. We will have Q&A at the end. Keep your questions to 30 seconds. I will request the speaker to repeat your question so that we have it for our live streaming audience as well. Thank you.
Thank you. Savita, we're starting a bit late, so it's 7:25. How, till when do you want me to go?
What's the?
We have our, we have
1 hour.
At least 1 hour.
Okay. Can people hear me? Okay. Yeah. Okay. All right. It's projecting. Okay, we're in business. All right. Thank you for coming, all of you. It's a pleasure to be back. Thanks to SF Bay chapter folks who keep inviting me to come back. Second year, as Savita was saying, and thanks to PayPal and SR for hosting. It's a beautiful location and nice venue. My first time here at PayPal. Well, so today I want to talk about AI, specifically how to put AI to work for enterprises. We all know we use AI in our day-to-day lives without even actually realizing it, in our phones, in our Google Maps, search engines, everywhere, and we've been using it for several decades now, whether we explicitly call it AI or not. So in consumer space, AI is all pervasive, more or less. Of course, in enterprise too, in enterprises too, it's being used pretty widely, but I want to talk about some specific things about how to really make AI to be used more broadly in enterprises, and what are some of the important factors that one has to take into account when building AI models for enterprise use, and what does that mean, and what are some of those factors that are very important that may be somewhat different from putting AI to use in consumer space. Not significantly different, but there are definitely differences. So I want to talk about that from my own experiences of building AI models for enterprise use. As you all know, I work at IBM and IBM's Watson division, and we build AI models, and I'll tell you more about that. And our customers, IBM's customers, are enterprise customers. So when enterprises use AI, what are the concerns? And those are the things that we are concerned with in making it work. So if you look at, and I'll talk about different types of AI applications. So if you look at different types of data in enterprises, actually, there is structured data, semi-structured data, and unstructured data. Structured data has been well studied, although there are interesting challenges there to work with. Semi-structured data, somewhat studied. Unstructured data hasn't been tapped into a lot because it is so unstructured, it is so hard, it's human written, human generated. When I say unstructured data, it could be speech, it could be text data, it could be images, any kind of things. And there is a lot of potential in there, but enterprises haven't been able to tap into that broadly up until now because of a number of reasons. The difficulty in processing that type of data, and the availability of compute resources, and so on and so forth. And when you actually put all of these types of data together, the structured, unstructured, and semi-structured data types, it becomes even more interesting and challenging as to how do you deal with it and how do you derive insights from it and make sense of it. So today I'll focus more on the unstructured part of it, because that's where some of the interesting challenges are, because the structured world, databases world has been well studied, although there are interesting challenges still there. So when I talk about AI, today I'm talking more about the AI applications that are being built to tap into the potential of the unstructured data. So you can see some of the AI applications that people are building these days. So I'll take you through some of them just as an example. So if you look at chatbots are a very prominent way in which people are starting to use AI these days. You call into a call center, it automatically gets redirected to chatbots, and for some low-hanging fruit type of questions, easy to answer type of questions and more frequently asked type of questions, they are able to already take calls already. So that's one example of AI application. There is, of course, the first one that I'm showing is really about invoice processing, digitization, the optical character recognition, OCR types of things. That has been there for a long time. So moving on to the right, AI is being actually very widely being used in healthcare types of applications, in healthcare domain as doctor's assistants, as nurses assistants, and in radiology, in processing different types of radiology reports and detecting anomalies in it, and so on and so forth. So a lot of applications in healthcare. In legal domain too, attorneys are able to put AI to use in doing legal research for them. That is, you can put AI to use to process large amounts of documents and legal laws and help do the research for you, saying which laws apply for which context and so on and so forth. Social media monitoring. People are talking about their preferences, their interests, and a lot of things, and they're actively being monitored by companies to better understand the sentiments, get product feedback, and so on and so forth. And so on. In retail, of course, autonomous cars, in facial recognition that you are starting to see at airports, and even in different kinds of applications different kinds of situations where AI is used to provide decision support, be it in employment, resume screening, or student application screening by colleges, and those sort of things. And I purposefully chose these set of applications to talk about AI in business, because there are actually a lot of interesting combinations of things going on here. Some that have societal impact, regulatory impact, like the autonomous driving and the credit application and so on, because they touch humans and they touch legal laws and on roads and such. There are a lot of interesting ethical, security, and societal implications. Some that are more sort of private, personal, preference related things, like in retail, where individuals are getting very personalized recommendations. AI is being applied there, and there are concerns about privacy and those sort of things. And chatbots, which are somewhat sit somewhere in the middle. They are not so sensitive. I mean, as long as you can process enterprise data that's not so sensitive, you can put AI to use there without too many concerns. So it's a good mix of a range of things that are that you can see on where all AI can apply. So given that this is the kind of applications where businesses are putting AI to use, the question comes as to, okay, so what is behind the scenes? How does one go about building the models, and what does it take to actually put these things to use? So here I have a demo. If it plays, so this is a chatbot that we have built that takes a call from a caller and automatically provides a recommendation. It's you may have seen instances of this, but it's interesting nevertheless. I hope it's audible enough. Let me play it. Can you hear it?
Hello. How can I help you?
Hi, I'm calling about my phone charger issue. It isn't working. Can you help me? My customer ID.
So the audio is not so visible. I mean, the audio is not audible. Let me see if I can. Is there a technician who can help me with the audio? Okay, where is the mic?
Hello. How can I help you?
Hi, I'm calling about my phone charger issue. It isn't working. Can you help me? My customer ID is 13345.
Thanks for reaching out. about the issue.
Can I put my isn't working? Can you help me? My customer ID is 123456.
Thanks for reaching out. Can you give me some more detail about the issue?
When I put my phone for charge, it just isn't working, which is ridiculous because it's a new charger. I just bought it 2 days ago.
I'm sorry you're having issues with charging. What kind of charger do you have?
It is the charger that came with phone A. It worked on the first day, but stopped working the next day.
I see. Sorry to hear that. Let's try a couple of things. If you are using a wall outlet, could you check to see if the wall outlet is actually working by trying to charge something else in it?
Let me see. Oh, I think I powered the switch to the wall outlet off by mistake. I just turned the switch on and tried charging. It is working now. Thanks for the tip.
Great. Happy to help anytime. Do you need any more help today?
No thanks. Bye now.
So this is a very simple example, but I wanted to show this to illustrate how many things have to come together when you put a chatbot like this. So there is the speech aspect of it. The person who is calling in is speaking. So there is speech to text behind the scenes, and the speech is getting translated to text. And once it's translated into text, that text there is intent recognition going on what is it that this person is actually calling about. What is the problem? And so the transcript is getting shown, and once the intent is understood, then the system is looking up in its knowledge repository to find what the actual resolution might be, and it's automatically able to distill all the customer ID information and also some of the sentimental kind of statements the customer is making. It's ridiculous and all that. Those are all not important to actually go find the actual resolution. In fact, it may confuse the situation even more. So do a lot of cleaning up of that and only take the informative aspects of it and pass it to the knowledge repository to pull the correct response associated with that problem, the intent. And when you have that, construct a response and have it be played back with text to speech. And behind the scenes, a lot of things are, the system is showing how, what is the transcript in real time, and what is the sentiment of the person, and what kind of suggestions are coming, and so on. So this is just a simple example to show what kind of things have to come together to build these AI applications. So the behind the scenes, it's building blocks like this. It's speech to text technology, natural language understanding for intent recognition. It's natural language classification. In this particular example, not all of these are showcased, but there is search and retrieval happening, and you want building blocks like image recognition, and something that manages the dialogue, and something that helps you understand the tones, the communication tones associated with the particular speech. Is the person very frustrated, annoyed, satisfied, excited? Which one is it? And the personality of the individual. What kind of personality is the individual reflecting in it, so that you can personalize conversations and recommendations. So there is a lot of these building blocks that have to come together to build any AI applications, and there are many companies and vendors who are building these types of building blocks. But just having these isn't enough. There are many things when you take all these building blocks and start building the actual AI models. Many more things have to come together, and that's what I want to spend some time on. But just a little bit of background on AI models. Several of you are probably neck deep in actually building AI models. Before the talk started, I heard a few people talking about features and feature extractions and so on. So you're probably already quite familiar, several of you. But in case not, AI models can be of many kinds. If they are machine learned models, they need to be taught, right, with labeled data, giving labeled examples. Say you give cats and dogs pictures and you label them as cats and dogs, and you label enough of them and give it to them, the system understands to discriminate between them and classifies them. That's a very classic example that people talk about machine learning. But machine learning is not the only AI. There could be rule-based systems are AI too, and knowledge representation is AI too. So AI is a much broader field than machine learning alone, although these days it has become more synonymous, where machine learning scientists have pretty much taken over the field of AI, and AI has become synonymous with AI. But many of the ones that I have talked about, the speech recognition, natural language understanding, they all have elements of machine learning models, and so they all need to be taught. A pretty standard life cycle of building any AI model starts with data collection, preparation, getting data, preparing it with labels and in the right proportions for the kind of distributions that you want for different labels that you're trying to train it. And of course, the feature preparation, is you tokenize the words. If it is speech, then you create the phonemes associated with it. You have part of speech, everything identified. Prepare as much as many of these features as possible. Although these days with word embeddings and sentence embeddings types of things, you don't necessarily have to spend a lot of time preparing yourself. And then of course there is the model training, which includes selecting the right kind of machine learning algorithm, right kind of architecture, hyperparameter tuning, and those sort of things. And then you test the model for its accuracy and establish the accuracy metrics, be it precision, recall, F measure, mean absolute error, whatever your metric is. And there is a lot of things that have to come together in terms of service enabling this AI model to deploy it on cloud and to have enough instances of it running containerized so that it can take enough loads and so on. So there is a lot of things that happen, and there is a life cycle associated with building an AI model. But this is just the beginning of it, right? You build such an AI model. Is it the end all? Once you have built a model, so let's say to understand speech, or a model that can take credit applications and can make predictions on whether to grant credit to this person or not. Is that it? Is its accuracy going to be at 100% that you want on day one when you build it? Is it going to be able to understand the intent if it is a chatbot of every caller with all kinds of accents, in all kinds of industry domains that you deploy? Say you build a chatbot for an insurance company and you take it and deploy it in a financial services company. Would it be able to understand the language, the vocabulary of a financial services company on day one and be able to perform at the same level of accuracy like how it did in an insurance company? No, there are many interesting challenges that we have to really face and to fine tune these models to get them to really work at the levels that an enterprise wants. And that's what I want to talk about. So race facts is just a mnemonic that I coined. Each letter stands for something that is important. I'm not going to talk about them in the exact order, but each letter stands for the following. So A is for accuracy. The models have to be accurate, and we'll talk about that. Take each one and go into the details. They have to be accurate. They have to be continuously learning. That's because they're not going to be perfect on day one. And if there is no mechanism for them to learn, like how humans learn, right? We hear somebody speak, we catch a new word that we don't know, we learn about it based on the context, or we go look it up and we learn it. Next time somebody uses that word, we know about it. Machine learning models have to be able to do the same. Otherwise they are stale and they're stuck at a particular level of accuracy. Consistency. As they are continuously improving and learning, it cannot be that the accuracy wavers, as in on the same prediction, it made a right prediction last time, and after some more iterations of learning, now it gets them all wrong, but it gets something else right. That is quite possible. When you build statistical models, you cannot guarantee accuracy exactly on the same set of samples, but there will be domains where you cannot go back like that. So there's consistency is required, as in the model is continuously improving in the right direction, and hopefully on all the same samples. Fairness, and we'll talk a lot about this. AI models have to be fair. There is a lot of questions being raised, rightly so, on do AI models take the same kind of biases that whoever is building the model, or are they voluntarily or involuntarily learning biases, and how do you detect those, and how do you make sure that the models are as unbiased as possible? Transparency and explainability. So if you build AI models with deep learning models, we don't necessarily have full traceability and understanding of what exactly is happening inside of it. So what if somebody comes and says, why did my loan application get rejected? What is the rationale? And we can't just simply say, oh, it's because your alpha or beta is such and such and it's below threshold. There has to be some rationale, especially in some industries that are regulated, you have to be able to explain it. And depending on the type of models that you use, type of algorithms that you use, you may or may not be able to explain it. So there is a lot of work that's going on in the field of AI and machine learning to be able to explain the models and provide that kind of transparency. So we'll talk about that. Accountability. Again, you have to be able to explain and also have the history of how this model has performed over different versions that it has been in production. And if you don't have that history of it, if you are audited, there could be a lot of problems, again, in regulatory environments. And robustness. Models have to be robust to be able to deal with all kinds of adversarial attacks that may be, targeted at it. So there are, when you build an AI model, for fun learning examples, it's great. But when you actually deploy them in real world applications in businesses, all of these factors have to be taken into account, and these models have to provide guarantees on many of these things to certain levels with service level agreements and such. So how do you go about doing that? What are the kinds of techniques and tools and strategies that you have to employ as AI developers or organizations that are embracing AI into their applications is what I'll be talking about in the rest of the talk. So let's take each one at a time. Accuracy. Again, I think many of you may be familiar with it. These are some of the metrics that are typically used in evaluating the goodness of an AI model. It's precision, recall, F-measure, accuracy, false positives, false negatives, mean absolute error. If it is speech to text type of thing, it's word error rate, and so on, right? Sentence error rate. So there are different kinds of metrics that are used depending on the model. So when I talk about accuracy, I'm talking about these things. So there is typically measured on 0 to 100. And if it is a goodness measure like precision recall, the higher the better. If it is the opposite like the word error rate, the lower the better. So I want to talk about what it takes to improve accuracy. So you build a model, every machine learning algorithm actually has some way you can do different kinds of validation, cross-validation testing and put out the confusion matrix, and you can measure with whatever metrics you are measuring, you'll measure the base accuracy. You got it. You know how to do it as a data scientist and a machine learning scientist. The key now is how do you make sure that this model has the hooks and ability to learn and improve. Now, you can always say, okay, the way I would make it learn is I'm going to take some new data that just arrived. I already have some data with which I trained the model, so I'll put it all in, and then I'm going to retrain the model from scratch. Well, that's a crude way to do it, but a lot of times you may not, if you deployed a model, say one company built a model with the data and they gave you the base model and it's deployed in a customer environment. Now the model is in a customer environment and it has to learn within that environment. And the company that built the base model may or may not want to give the client all the base model training data. So it has to be able to learn with the delta data on top of the base model. So that means when AI models are built, you have to build with these hook points to customize them. And that customization, call it transfer learning as a concept, but has to be able to learn on top of the base model without needing the original data. Otherwise, you always have to bring it back to the original developer of that model and use all that data and retrain it from scratch, and it may take several hours. What if a speech model is built with 1,000 hours and it takes several hours to build it? Do you want to wait that long to retest it and do regression testings and so on? So here I'm showing this phenomenon of building a base model versus a customized model. So this is the example that's shown is a piece of text, the dictation that the doctor is making. And if you take a base model, there are a whole bunch of mistakes in it. I have a live demo. I'm trying to decide if I have the time to show it or not. Maybe towards the end, if I have time left, I'll show it. But so the idea is that the doctor is dictating, and the speech to text system is working and is transcribing, and it made a bunch of mistakes. Because it's the base model that's been trained with normal conversations and news articles, what news audio and those types of things, let's say, and it's not been exposed to lot of healthcare domain vocabulary and such. So it made some mistakes, and so it lower sternum is the word, and there I don't know if you can read it properly, highlighted in yellow. The first one says lower sternum instead of sternum. Elevated proponent, that is also a mistake. Good con or syndrome, it's a coronary syndrome. Full sort of colitis, again there is a mistake there, it is supposed to be something else. So the original base model made some mistakes, and that's probably okay. Actually, it's not the end of the world. You don't expect a speech model that somebody builds to be perfect when you deploy it on day one in a completely new domain. But the key here is that this model now has to improve. How do you improve? All I want to be able to do is to take my text, the right text, just for a small sample, feed it in and say, hey, here is some vocabulary associated with this domain. Learn based on this vocabulary, rebuild the model, deploy it, all happens within a matter of few seconds, and you are able to now submit the same audio file and it will correct its mistakes, right? That is what I'm talking about when you say customization. And in fact, in the live demo that hopefully I can show, that's what it does. It's a matter of seconds, right, where you submit a small paragraph of this with a few vocabulary things in it, and it starts to learn. And you don't have to retrain the whole speech model, you don't have to go back to the original developer of the speech model and so on. So in an enterprise context, imagine that's what needs to happen. You build a model, it has to have all the right hooks so it quickly learns from the data. So on the left side, yeah, lower sternum was a mistake to lower sternum. It got fixed after I submitted that small data file and read it. Acute coronary syndrome, ulcerative colitis, and troponin was the protein instead of proponent. So these kind of things are very easy to correct. So the point is that accuracy will be what it will be on day one when you build an AI model. Hopefully you have collected the right kind of data in right amount of proportions for the solving the particular kind of problem, but it will be what it will be. When you deploy it, you will face challenges, you will face surprises. It won't be exactly at the level that you want in each domain, but in each domain it has to be able to take the data, delta data, and learn. So the key insight that we got as we were doing this is that when we talk about AI, there is this notion of base model, right, which is what consists of the general language vocabulary and those types of things that anybody who wants to be a vendor in the space of AI can use to build. But then on top of it, we can build industry models, let's say for financial services domain, for insurance domain, for retail domain, and so on, and keep them ready. On top of it, still, when you take those models and deploy it for specific companies, there may still be vocabulary and such that is very specific to them that the system still needs to learn to improve its accuracy. So it's a continuous learning process, and the idea here is that you want to narrow the domain so that the accuracy of the model can be increased. And that narrowing of the domain is basically, instead of trying to solve the whole broad AI problem, you are trying to get it to the narrow AI problem, right? The base model is solving the broad AI. Broad AI is a very hard problem to solve. So we have some decent base, and then we start to narrow the domain and build models that are very specific to those domains. And those models now, when deployed in specific applications for specific industries, they'll start to get the job done. They may work only in that environment, that's perfectly okay, that's the state of the art, that's where we are. And if you're familiar with this notion of learning curves, right, typically when you build AI models, you draw these learning curves. You have on the x-axis the amount of training data, and y-axis you are plotting the accuracy of the model. Typically the more the data that you have, the better the accuracy, and at some point it plateaus. So the first one is showing the base model learning curve. The idea of narrowing is that you can start to ride different learning curves and accelerate your pace of learning by narrowing the domain. So for domain specific learning curve, for customer specific learning curve, now you are quickly moving up and riding different learning curves. So that's what this idea of customization. So when you build, the key thing that I want to kind of strategies for achieving desired accuracies in this letter A accuracy that I want to talk about is the following: that build broad-based AI models, whatever the case may be, but build customizations and hooks that are required so that the model can learn and improve its accuracy on the job. So let's talk about the continuous learning, very related to the point that I made about accuracy. The models have to be able to learn continuously. When we started to learn to ride a bike, we didn't get it on day one, right? We fell many times, but it takes a few attempts to get there. So here is a continuous improvement life cycle of an AI model. So there is an AI model, it starts to make predictions, there is some input that's sent to it, you have to be able to explain the results, and that prediction that it makes, now you can start to observe with other observer models and say, did I get it right or wrong? Because the way you know whether you got it right or wrong typically is by asking a human, but that's very time consuming. You cannot, for every prediction that the AI system makes, ask a human to judge it, and then we are there forever getting those feedback loops to further feed that data back into learning the model. So we have to have some way of automating this process of predicting whether the model got it right or wrong. And so there are many techniques. Again, this in itself could be a talk for 1 hour or more. So I won't unfortunately be able to get into all the details of it, but the idea here is that in the whole entire life cycle, there are many places where we can apply AI to actually build AI models. So it's data for AI, AI for data, AI for improving the life cycle of AI itself, and so on. So it's like this recursive thing where you need to apply a lot of automated models, automated ways of labeling the predictions to be right or wrong, and feeding that back into the original AI model for continuous improvement. And along the way, you also want to make sure that you are not taking every piece of data that comes along and feed it back into the AI model, because then you are, I'll talk about that in a bit, you may end up drifting the model. You built the model for something, let's say for predicting, doing a good job at something. People are starting to use it for some random purposes. You take all that data, you clean that data, put that in. Now you have started training this AI model with all kinds of data that you don't know what its purpose is anymore. It will start to actually drift in ways that are unforeseen and unpredictable. And that could cause a lot of problems. And there are specific examples of unfair predictions or biased predictions that the system will end up making, and we'll talk about that. So the point with continuous improvement, here is some example that we did for sentiment. So we divided up the sentiment prediction. So the idea is that you have a text sentence, you feed it into the AI model, and the AI model predicts whether it is a positive sentiment statement, negative sentiment statement, or a neutral statement. Okay, so we took the inputs that went into the sentiment model, divided that up into how many tokens, what is the length of the text. Depending on the length of the text, whether it has 4 tokens to 8 tokens, 8 to 12 tokens, and so on, we plotted the accuracy. So we noted that when we have a long sentence, like 2 or 3 sentences combined in the piece of text, and we fed that into this AI model, this particular one was not doing so well. Its accuracy is only 56%. This is the left side of the graph that I'm talking about, instead of 71%, which is like for small pieces of text of 4 to 8 words. So what we ended up doing, so this is a strategy that I'm talking about for continuously improving the models. What we ended up doing is that, so it's not doing so well for long pieces of text. So maybe what we ought to be doing is actually build a separate model just for that long piece of text, and when the input comes in, detect how many number of tokens there are. If it is something more than a certain threshold, send it to this other AI model, and the accuracy for that specific micro model is at 86%. So which is pretty good, better than even what we started with. So what exactly I'm trying to say, and how am I connecting it to this idea of continuous learning? There are many strategies to continuously improve the models. Not only you customize, create a hook point and let it learn with the delta data, but you may have to look at whether you need to build specific micro models for specific types of input data that comes in, and take all of those things into account and build the feedback loops to continuously improve the AI models. So here is a summary of that, what is the strategy for improving AI models. So, enable continuous improvement, of course, with customization. That is, the model should have not only a train API, it should have a retrain API or a customized API that is exposed. And by expose, I don't just mean to say expose it, but do it in an efficient way that it can take the small amount of data and learn. And we have to be very diligent for the model to continuously learn. We have to be very diligent with doing the error analysis. So, after every iteration of predictions that it makes, we need to be able to classify how many of the predictions it made are right, how many are wrong, which ones are wrong, and why are they wrong, what are the weaknesses of the model. Like in the case of the sentiment, where we found out that the weakness was when you send long text, it is unable to do a good job of it for whatever reason. Then go investigate it, and if you need to, if the same model that you have built is not good enough to solve that problem, maybe sometimes you have to build a specialized model to address that particular problem and deal with it at an architectural level as to how to process the input in a way that you use the right kind of model at the right for the right input. For this continuous improvement life cycle of AI models, one of the critical things that becomes a bottleneck very quickly is this ability to have labeled data in large quantities, even to feed back. So, when I say expose the retrain API, even the retrain API needs to have labeled data. So, getting that labeled data in every iteration could become a manual process and an expensive process. So, trying to automate that again is, if possible, is important, and in order to do that again, you may need to have additional AI models that are unsupervised to help you label. So, moving on, I will talk about fairness. So, this is a topic that is of great interest to popular media, especially whenever I am on panels or whenever I am interviewed, they always ask this question. Because it always perks up audience's interest. Everybody knows about Microsoft's chatbot that was released and had to be pulled back because it learned a lot of racial slurs and all that. So, people talk about that and ask questions about, well, you are putting all these AI models that are being used in college application screening, in credit application screening, in facial recognition and so on and so forth. What about biases? Yes, that is an important concern. Undesirable biases, when I say biases, because bias by definition is actually an important and an interesting thing. In a statistical model, bias is the foundation for actually optimization. When we talk about bias, I am talking about undesirable bias. I won't today get into the details of whether humans are unbiased and fair, therefore is it fair to expect AI models to be totally fair and unbiased. That's a discussion topic, interesting one for another day. But what I want to talk about is from a technology perspective, what kind of precautions can we take to make sure that the AI models that we build are as fair as possible. Again, the fairness being defined by whoever is building the model according to their definition of fairness. So, there was this article, again some of you may have read about it. It's been about a year and a half now, I would say. This was a piece of work that was done by researchers. They wrote a paper, and New York Times picked up that paper and they highlighted it. Basically, it's the research was done. The link to the paper is down there by researchers who tested the image recognition software of multiple companies by feeding it a bunch of images, several of which contained African women's faces, and most of the facial recognition systems actually ended up doing a very poor job of detecting African women's faces and classifying them. And this was highlighted as a bias by the various AI models in the articles, and raised a lot of uproar and discussion in popular media and in academic circles as well. And we went back and introspected our own facial recognition software, and a lot of lessons learned from this episode. Basically, undesirable bias could get introduced in any number of places. It could, if you look at the AI life cycle model, be it at the time when you set the goal itself, if you don't set the goal that these types of things have to be recognized at this level of accuracy, right there you have not defined the goal for the AI model properly. Then if the goal is not clear, of course the model will be unclear about what it needs to do a good job on. Data collection, if the data collection is not commensurate with the goal that you have set, you can be introducing a lot of biases there. And for whatever reasons, if there are not enough images of a particular category, then you could be introducing those biases by feeding in fewer of those labels, and therefore the model is unable to learn to predict those category labels with the level of accuracy that is desired. It could be coming in training bias, testing bias, feature bias, model bias, all kinds of areas where biases could be introduced. So the bottom line is that when you don't know where you're going, all roads will lead you there. When you don't give a goal to an AI model, then you cannot blame the AI model for being biased. So the question is, how do you define an AI, a goal for an AI model? If you go back to traditional software engineering, right, best practices emerged over a period of time. People said the best way to build a great software is by writing test cases first, right? You write a test case according to the requirements, write enough of them that cover it, build a piece of software, make sure that it's working on all those test cases as desired, then you know that you have built a system that actually works as per requirements. When we build AI models, we have to follow, there is no reason to forget the best practices that we have learned from software engineering discipline, right? So define the goal clearly. How do you define the goal? Create the right type of test data sets and set thresholds on the levels of accuracy that you want. And don't compromise on releasing the models if it doesn't work on those test data sets for the level of accuracy that you want. But then, as I said, that's not going to be it. For building practical models on day one, even if the model passes on all the test cases to the level of accuracy that you want, doesn't mean that it will do the right thing in the field when you put it in, because there is no way that you can possibly collect all types of things that the model will be exposed to in the right proportions and to train it on day one. So again, all these points are interrelated to accuracy, continuous learning, customization. They're all very interrelated, and same goes for fairness too. In order to build a fair model, you have to first be very specific about the goal, create your test data sets, but be prepared to iterate and improve the models on an ongoing basis, but clearly identify and know what is the goal. Don't let the model waver into so many different directions that you don't know what its purpose and goal is again. So some strategies for mitigating unwanted biases. There are a lot of, I hope you realized by then, I'm not doing a deep dive technical talk on one topic. What I'm doing is a more sort of best practices and what it takes to make AI work for enterprises. So it's a broad-based methodology type of a talk, because I know a lot of people talk about, and I saw some of the advertisements on, very deep on time series anomaly detection. Those are all great. I think we need several of those, but we also need to disseminate this knowledge at a methodology level, what it takes to make actually AI work in enterprises. So today my talk is very focused on that. So that's why I'm not going deep into each one of the either fairness algorithms or algorithms to improve the accuracy, customization, some other topics for other days. But so I'm in this broad-based view, right? I want to give some high-level best practices on each one of these topics that I'm talking about. So fairness, how do you deal with it? Set clear goals. Start with test data sets, what's possible. And another thing, declare your biases, right? When you build an AI model, if you explicitly state what kind of data it's trained with, in what proportions and what labels and so on, people know what they're getting. It's like the nutrition labels on nutrition snacks, right? When you buy a snack bar in a vending machine, you know exactly how many calories it has, how much sugars it has, and carbohydrates and so on. So you are making a judgment and decision based on your body type, your hunger levels, and all those things, and you know what you are eating, what you are putting into your body. Same thing with AI models. Actually, a lot of work is emerging in this area of AI fact sheets, and where specifications of what AI models are built with are going to be clearly specified and declared, and they come attached with the model. So whoever is the receiver of the model, or whoever is the model buyer of the model, will know exactly what it's built with. So I call that declare your biases. At least you are telling the world what the model is built with, what it's been tested to work with, so people know what its limitations are and what it's good at, what it's not good at, and they'll know what other data to supplement to it in order to improve it further. That you can do to some of the known biases, but then there are a lot of unknown biases that that you may encounter, and this happens all the time. You cannot, some standard attributes like race, gender, age, location, salary, these are the things that we can watch for discrimination on. But there are a lot of times many things that show up, sometimes names associated. If you take, Twitter data, this data, and train an AI model, during presidential election time, we noticed our sentiment model would just when the names of presidential candidates show up, Trump or Hillary or any kind of candidate you take, it will say sentiment is negative or positive. And that's an unwanted bias, and it's not related to any of the known types that we monitor, but it's something that crept up, and it may be very time based, but it crept up because of the data that we were pulling. And we have to watch out for those types of things and unknown biases, and we need actually techniques and approaches when we build AI models to configure them for us to be able to catch those types of things. So there are many nuanced details to building and catching these types of things for not only known biases but unknown biases. And debiasing techniques, there are a lot of techniques that are in literature that are being applied. IBM itself has put out this AI Fairness 360, which is a suite of algorithms that implementations from various different papers, including some of IBM's own. And it's a suite that's available for anybody. It's open source. Anybody can go and use some of these algorithms to debias their AI models. If you are building them, feel free to check them out if you haven't already. All right, transparency. I'll go through some of these things quickly. Transparency. How transparent should an AI model be? Should it be explainable completely or not? You could argue is somewhat of a philosophical question. When you go to a doctor and ask the doctor to prescribe a medicine, you don't necessarily exactly ask for all the details on how exactly the drug works. How does it break down in your body, and what are the compounds, how does it react with whatnot. You trust the doctor to do the right thing as long as you show what other medicines you are taking, and the doctor prescribes some drug and you trust it to not react with other drugs and you take it. Are you asking for explainability there? So is it blind trust that you have to put in AI models? Some people argue that, well, maybe 100% explainability, transparency is not required, but there are domains and industries where it is, and there are use cases where it is. So for example, let's take a chatbot. In a chatbot, if it got the intent wrong, and instead of answering the question for password reset, let's say it gave some other response. It's not the end of the world. You are a little bit frustrated, and maybe the call will get redirected to a human on the line. For such models, is 100% explanation, transparency required? Maybe, maybe not. It depends. Whereas an insurance application or a claim application for insurance, those types of things, when you accept or reject some things, people have the right to question why that decision was made, and legally you are obliged to provide some kind of explanation and traceability and so on. So arguments go both ways. It depends on the use case, it depends on the industry. So explainability is a very important aspect of understanding and actually putting AI models to use. So what are some of the strategies for dealing with this? If you are using deep learning models, there are algorithms and techniques that are being developed to be able to explain the models better, and this is after the fact. You poke the model with enough number of data samples, and based on the behavior that the model is exhibiting, you construct some kind of an understanding of how the model is behaving. Basically, that's the best you can do, because by definition, deep learning model is with deep neurons. You don't necessarily, you cannot interpret the hypothesis that it is making internally. So the way to do it is after the fact, you query it and construct its behavior and use that as explainability. So that's one of the techniques that's being used. Among other things actually that are not much talked about are using more transparent type of rule-based systems on the user front, which are generated by deep learning models. So deep learning models could be generating the rules which are then actually applied, and when something is not, some prediction went wrong or some prediction is in question, you can actually interpret it, say you can attribute the prediction that the model made to a particular rule, and you understand, hey, this rule fired, therefore this model behaved this way. Now, how did that rule come about? It could have come about from a subject matter expert who has created it, or it could have been discovered by a deep learning model, right? There are actually models that are being built in which where you put deep learning to use behind the scenes and expose the rules to the users, because they're a lot more interpretable and understandable, and that's AI too. Not many people talk about it, but it actually has great scope for research in domains where interpretability, explainability is very important. All right, consistency. Statistical models do not guarantee consistent improvements. That's definition. You know, there is no way you can guarantee it. On the same label, same sample, you could have predicted it to be positive sentiment, and in the next iteration it could predict it to be neutral sentiment, and there's nothing much you can do about it. Again, it goes back to the use case and the needs, right? If you have the need where you have to be able to consistently improve, if a subject matter expert gave a rule, painstakingly said this rule, this is the reason why this needs to be this way, you take that into account. Somehow you have to respect that in that particular domain. You cannot just simply take that rule, try to create some data corresponding to that rule, and hope the statistical model will actually capture it. And next time around, it makes a mistake. The subject matter expert who gave a rule for their company, for their domain, will get super upset. And this happens all the time when we deploy AI models. So there are choices, architectural choices and algorithmic, and also fundamentally these choices that we have to make, whether it's a rule based or a machine learning based, or it's a combination, and if so, how do these things work together type of thing, in order to guarantee consistency. Again, this depends on how important that is. Again, in chatbots type of things where intent is being recognized, sometimes it gets it to be, you know, this intent, sometimes it thinks it's that intent, it's okay, it's not the end of the world. But in some domains where it is very important, consistency and rules have to be honored and respected, you may have to take different approaches, and you can't use the same hammer for, you know, for everything. Oh yeah, this is my favorite quote. I don't know if you have seen it. Let me see how I go back. So this is for those of you who are Sherlock Holmes fans. Sherlock Holmes, you know, I think in one of the first books says, there comes a time when for every addition of knowledge you forget something that you knew before, because you have only so much memory. So this is what happens to AI models too, right, if you don't take proper care. I think I talked about all these things on what are the strategies for dealing with consistency. Yeah, you have to, you know, subject matter experts' opinions are important. You have to log the payloads, as in the input that's coming into the models, to take that into account, to continuously keep on improving the models. Okay, accountability, and I kind of combined drift with it. Accountability, what does that mean? I alluded to it a few times. You build an AI model with a certain amount of data and say certain proportion of labels for positive, negative sentiment, or for certain, you know, features, for certain faces and so on, and you put the model to use. In production, it's starting to get more and more data, and you take some of that more and more data that it is being asked to predict, and feed that in by adding some additional labels, and the model is learning. Slowly you may be adding more and more data, and my model now is good at, instead of being good at here, on this it's good here, and it's good here, it's good here. After a few iterations of learning, my model is no longer good at that, it's actually good at this. But the question is this what you really want? So that is called drift. Things are, you know, you knowingly or unknowingly, when you are doing continuous improvement of models, you are taking the input that's coming into the model. And if the input is exactly in the same domain, exactly for the purposes that it is meant for, that's fine. You still have to very carefully monitor. You can't take every piece of data that comes in and feed it into the model and say, hey, I'm improving my model from iteration to iteration. No, the model could be completely deviating from its original intent. So, and that also kind of is related to accountability, as in you want to kind of keep track of the history of the predictions that it's making on the original test data sets. On it, with every new addition of data that you are adding to it, you create new test data sets. So the old plus new test data sets, you do regression testing on all those test data sets and plot the accuracy and make sure that the model is actually within the parameters and boundaries of what you wanted it to be. Otherwise the model is drifting, and how do you deal with it? Yeah, you have to really kind of keep track of the data lineage, the input, the training data, the testing data, and everything that's going into it, the labels, who are labeling it, and how much, in what quantities are you putting it in. Keep track of all of those things and continuously observe and predict the model's accuracy on all the test data sets, not only the old but old plus new. That's the way to kind of deal with drift. Last one is robustness. So this is an example from this OpenAI adversarial research. So the original image that was fed in was this one on the left, which is washer dryer. But depending on how you take the image in different angles and directions, the model could actually get confused. What was originally a washer could become a safe, or it could become a loudspeaker, and so on. So it just depends on the angle. So the idea here is that you take the original model and create different adversarial examples from that original model using different types of techniques, and you feed those different samples to make the model more robust. So you tell, hey, when you take in this angle, this picture, and feed it in, it is still a washer. This one is also still a washer, it's not a safe, right? So when you take enough of those kind of adversarial examples, and they're called adversarial because typically, when you want to attack a model, you could be submitting those kind of things with different angles and confusions, and take the model in a different direction than you originally intended to be. So how do you deal with this adversarial? So monitor the data carefully, of course. Everything goes back to data. And you can create your own adversarial training samples, right, by generating lots of different, and there are many techniques and many papers that are talking about it, and there's a lot of open source code for adversarial sample generation as well. And there are other techniques like defensive distillation, train the model to output probabilities of different classes rather than the hard decisions about which class to output. But the idea here is generally, you watch out to make sure that the model is able to handle different kinds of corner cases, and you have trained it with different types of examples to make it more robust. So this is the cheat sheet. If you want to easily remember all the things that I mentioned, race your facts. Your is just your to remember, but race facts. And each one of the letters stands for one of these things. Robustness starts with R, then accuracy, continuous learning, fairness, transparency, consistency, accountability. So when we talk about AI in enterprise AI, right, these are all very important. It's not just the accuracy, which is what people talk about all the time. There are many other factors that we need to take into account. And this is what we have learned firsthand. And of course, these are some of the things that we are working on at IBM and Watson to help our enterprise clients to watch out for, and various tools and algorithms and things that we are building have these capabilities. So with that, let me end. If there are any questions. Yeah. How much time I have, and maybe we should start with some in the room first and then go to the online questions. You had one?
Yeah, I wanted to recommend a best practice for robustness, and that is to take the cue from the medical journals that don't allow significance testing with the p-values and require confidence intervals instead. I think most people know how to get the p-values for their significance when they measure their accuracy and other model characteristics, but very few working data scientists know how to generate confidence intervals from scratch. So I think that needs to be one of those open source libraries, so that every step along the way, I believe that if we did that, we would save a lot of time, because it's hard to count the number of degrees of freedom, which means overfitting is always going to be a problem. With some fancy library, you don't know if it's got an extra degree of freedom that's making you think you're on the right track when you're not. Confidence intervals and the ability to show the confidence intervals of prediction for a classifier and such is, I think, the way to get to that. So I'm not sure if that's a question. If it is, it's do you agree or not? Otherwise, it's a comment. Either way, thank you.
No, it's actually a very valid point. I totally agree with that, and we do definitely do that confidence interval, and statisticians know this fairly well. Data scientists should adapt it. I totally agree.
Yeah, so my question is, I have. I have been attending a few of these machine learning talks. My former employer is machine learning.
Can you hold it closer, please?
Boss?
Yeah.
So, for instance, I have been attending a few of these machine learning talks. My former employer is one of them. It seems what you described today is what everybody's doing. So, everybody uses the same framework. Do you see any standardization efforts to actually define all the things that you said in the industry, or would that come from the startups? Because this, at this point, this field is very fluid. I mean, you have zillions of startups doing this thing that you described. You have the leaders in the field like IBM, maybe HP, maybe Google. But everybody's kind of using the same techniques, but using their own definitions. Do you see any standardization happening, regulation?
So some areas of standardization it started especially around security and ethics, because that's the one that's most urgent and important, around privacy related to data. And among other things, I've noticed the biases, right, where you start to declare the specifications of AI models, declare and what should be the formats and what are the types of things that you would expose about AI models. So there is some work that has begun in that space. So these are some areas that are happening. So to your point, everybody is doing. Of course, startups always go at very specific targeted niche areas, and big companies have to deal with all of these things, not just one aspect of it or the other. But as a set of best practices, right? I would say it is still fairly, maybe Bay Area community and people who are very much in this space are familiar with all these things, but when we talk to our clients, several of these things are still fairly new. You talk about a retailer, talk about an insurance company or a financial industry, their primary business is dealing with the insurance plans or financial services and so on. Yes, they have large IT organizations, but they are just about exploring these, what can AI do for me, how can I optimize my business processes, and when I deploy these AI models, what are the things that I have to be concerned about. So the onus is on us as community to educate and to talk about this, and if you already know this, that's great.
But something that you said, for example, say XML, just totally different, right? So when people wanted to achieve data, they came up with particular formats that everybody agreed. Like in modes, for example, that would be nice to have, so you know what everybody's talking about.
Yeah, so
semantic segmentation model of faces, you say, hey, this is the format that we described that everybody understands common language as opposed to some specific.
Right. Right, as I said about fact sheets, some things are starting to emerge in that space, and companies are starting to create their own consortiums initially, and regulatory agencies are starting to look at nothing yet, but I think they're in the works. It will take a few years for them to settle down. Right, everybody doing their own, yeah.
Anybody else? Can I read out? Here. How does an observer model work?
Okay. So the observer model. The idea here is that when a model makes a prediction, you need to know whether it's getting it right or wrong. So a way to do that quickly and in large quantities is, first you take some of the model predictions and get them labeled by a human. Then you build a model with that this when this input came in, this prediction was right, this prediction was wrong. Take that and build a model. So that model is now has enough understanding of how this model behaves. So, whenever a particular input comes in, you not only send it to the original model, you also send it to the observer model, and the observer model will predict not the actual outcome, but it will predict whether this model is likely to get it right or wrong. So, that is the idea of building an. So, it is an AI model in itself. Of course, it will have its own mistakes. It is not going to be 100% accurate, and it will be sometimes right or wrong in saying that the model will get it right or wrong, but at least you have somewhat of an automated way in which you can classify the outputs of predictions an AI model makes and says, hey, this one the model is likely to get it wrong. It is actually related to the confidence interval comment that the gentleman made. So, if your confidence on a prediction is low, that in itself is an indication that likely you are going to be wrong in that prediction. Therefore, you put it in a separate bucket. If your confidence is high associated with the prediction, you put it in a one bucket and say, okay, I do not need to teach the system, the AI model, by feeding it more of the data corresponding to this, because it already is good at it, it is confident about it. So, no point in feeding more of that data. I am going to now take the predictions that it is getting wrong or is likely to get it wrong because it is low in confidence, and use those ones. Either I am going to get a human to label them or use some other automated techniques, but I am going to try and improve the accuracy of the model in the areas where the model is weak at. So, that is the idea. So, the observer model is really a model that is also AI model that initially takes some labeled data, but it is kind of sitting along the side and saying, hey, this one is likely to get it wrong. It is like betting, right? This winner is going to win, this player is going to win, this player is not going to win today type of thing. That is what the observer model does.
Okay, the next question is probably related to that, counter to it rather. Regarding the improvement model, what you just said, how do you get around the problem of detuning when adding incremental changes in TTI?
Sorry, how do you get around the problem of what?
Detuning your original model.
Yeah. Well, so it goes back to, so if you have continuous.
I understand the question, right? You make some changes to.
Right, I understand.
Then, but it negatively impacts the other.
Right. So, it's, if you haven't monitored it continuously to a point where you said you let it take whatever data came its way, and now the model from being here actually got here, now you have to figure out what to do to get it back to being good here, then of course you kind of have to trace back. That is when the lineage helps a lot. So, right, you trace back all the data that you fed in and say at what point in time it started drifting, which data should I remove from my training data, or which additional data now I need to augment to it in order for it to kind of go over to the direction that it needs to. So, it's very painstaking. It is, but what we can do is to build different kinds of prediction models and say, it's good at this, it's good at this. That error analysis is so critical. That is why if we fully understand where the model is right, where it's likely to make mistakes, and classify the errors, the type of errors that it makes. Any kind of machine learning course that you take talks about the importance of error analysis and classification of errors. So, you have to know whether it is, if it is a sentiment analysis model, we always look at whether it's making a polarity mistake, positive to negative, negative, or neutrality mistake, whether it thinks positive is neutral and negative is neutral, or is it a negation mistake. When there are double negatives or negations in a sentence, is it a mistake? So, you have to understand what type of mistakes a model is likely to make. So, once you have a good understanding of the errors and have a taxonomy of those errors, you have, when a model makes a prediction, when you know that it is likely to be wrong, you have to then immediately do further classification to say what type of a mistake is this likely to be. Either get humans to tell you that or build automated models to tell you that, but once you know that, then you have to prioritize which errors are more important for me to solve in the next iteration, because you may not have enough time, resources, or data to fix all of the errors in the next iteration. So, you have to prioritize those errors and say, okay, I am going to focus on negation errors because they are really embarrassing for me. So, or I am going to focus on polarity mistakes in a sentiment model because they are embarrassing, and you take corresponding samples where the model is bad at and feed it, improve it, and in each one of the steps we need to build in as much automation as possible, and that is part of AI working to improve an AI model in itself. But it is, yeah, it's that it takes a lot of hard work to make good models.
what if you don't have the original data to address where you drifted?
Yeah, no, this is so that's okay. So this is actually a very practical problem, and it happens a lot. Believe it or not, either because the original vendor will not give you the data, or the data is lost, which happens in enterprises. Any number of things could happen, and yes, of course, the models have to be able to learn from and correct from whatever that base is. So it goes back to, well, there are many techniques in transfer learning domain that talk about how you start with a base model, and in fact there is a lot of work happening in the distributed AI learning, where you have a base model that you don't expose what data it's trained with, and even different departments within the same company would not share data with each other. So you take data from here, data from there, and do distributed learning. So there are techniques that you can apply to undo only the delta parts or add additional things to adjust the models. But it's a very important question, and it happens all the time, where you may not have access to the base model data, and you still have to fine tune the model. So, but basically you have to work with what you have. At what levels, what layers are you freezing the model, at what layers are you actually able to start adapting the model, and so on. All these factors play an important role in doing that adjustment.
I have to when you address these incremental issues, like if we have addressed to one incremental issue first, and then maybe after some time some other incremental issue, any correlation between these two issues as well as the solutions for them? How do you deal with that?
Yeah, so this, as I was saying, it again, it's the process, right?
Different from what you,
yeah, it is the process. So when you have to have the test data sets, not only the old ones, but with every incremental data amount of data that you are adding to it, you create new test data sets, because the new test data set should include the new data that you are adding, and you need to be able to test the model on those as well. So you are continuously updating your test data sets as well as you are updating the training data sets, and you have to keep an eye on, how the model is behaving on what all things, and watch out for it when you go from one to the other. And along the way, you have to also document with data lineage and with all the performance, the accuracies and everything that the model is exhibiting on which data sets, and you have to constantly watch for the direction in which the model is going, and that is the way to see where it has gone from where.
It builds some correlation between these two. It builds some correlation between the incremental changes.
Once you have the predictions of on test data sets, you can of course do all kinds of analysis, statistical analysis, and derive your insights that you want from it, right? But you need that discipline to be able to compare old with the new. The new is continuously changing, but you have to also carry the old around, because you originally started there, and you're constantly evolving. So the evolution itself you need to be able to test as well. Okay, maybe one last question and then we can wrap up. Yeah.
When speaking about accuracy of your models, you were mentioning hooks, which can be used later to increase it, during continuous improvement. What are those hooks?
So that is the customization. Yeah. So the question was.
I think it's for people who are watching the video or whatever. So the question is about the hooks that you mentioned when speaking about accuracy of models. That for continuing improvement, we need to build in the hooks. What are those hooks?
Yeah. So the hooks are customization. Basically, it's the retrain API that I was talking about. So you have to be able to take smaller amounts of data and retrain the model. And in a traditional machine learning model, that's transfer learning techniques people talk about, right? Where you have the layers, the top layer, up until the top layer, you use those weights, and for the new data you train on top of that, and the top layer is the one that you are now retraining. So that's one technique in machine learning, but retrain could also be interpreted as a philosophy. If you're exposing rules to a user, then you have to be able to add a new rule easily, or delete a new rule. Delete a rule, existing rule, and or modify things accordingly, and you have to be able to expose those things to the users of the AI model. That's what it is. So in the more machine learning world, people understand the transfer learning technique and how to freeze up until the top layer and use the weights there and retrain. So that's what I'm talking about when I say hooks, and that needs to be exposed. It cannot just be something that is that the original developer of the AI model keeps and hangs on to. It needs to be something that's exposed so the users can do it themselves. And that would have been the live demo that I could have shown actually, that how you load a small text file and retrain it as a user of a speech recognition system, and it would have within a few seconds would say, hey, I now have a new model, try it on the new model, and it would fix all the sternum, stardom, proponent versus troponin, these kind of mistakes that it made in the healthcare domain.
Thank you very much, Rama.
Thank you.
Okay. Here we have a
Oh,
door prize drawing,
Okay.
and this is only for members.